All right, I'm back. We're on page 288. What I want to do though is scroll back to 287 for a second just to like review in case it's been like 5 days or something. I don't know when you're watching these videos. Who knows? What we just did was we just worked out that through this limiting process, if we start with 2 points and we let one point just slowly approach the other, it doesn't need to be slow, it could quickly approach. We let the other point approach the first point, then the slope of the secant lines through the 2 points, when we take the limit, becomes the slope of what's called the tangent line. So it's the slope of the curve, the exact slope of the curve at exactly 1 point. This is a very new idea, but taking these limits will allow us to do that. So let's actually sketch it. So I'm going to write the equation of the line through the point to f of 2. So if you remember, f of x we said is x squared minus 1. So f of 2 is 4 minus 1, so 3. Then I've kind of alluded to it many times. There's notation for the slope of a curve at a point. And in this case, we can say it is f prime of 2. So that's slope. You're going to use that a million times. Eventually, you use it so much it almost becomes meaningless. It always has like a lot of meaning, but we found by taking the limit, so maybe I'll just write it out. It's the limit as h approaches 0. What? As h approaches 0 of f of 2 plus h minus f of 2 divided by h. We did all the work and we got 4. So we know that the slope's going to be 4. All right, so what we're supposed to do is carefully graph the function and the line on the set of axes. It's so hard to graph a parabola. Like I regret that I'm having to do this. Here and here. And then at 2, I know it's 3. And then it'll be here. At 3, it's going to be 8, which you can like barely even fit. It's just parabolas grow so fast. All right, so killing it. And then kind of lost it. And then on the important side, struggle is real. Okay, I think that's my graph. I don't know, that's the best I'm going to do. So what I'll do is I'll switch colors at least. So now what I need to do is, I never wrote the equation of the line. Look at me, not answering questions. Okay, the equation of the line, we're going to use point slope, obviously. So it's going to be y minus 3 equals 4x minus 2. Okay, so this is called the tangent line. This is a tangent line. Tangent, same word that we use in trig. Secant, same word. Tangent, same word. They're related. I leave it up to you to figure out how. The internet can help you a lot with that. So now I need to sketch in this tangent line. So this is part of the beauty of point slope form, right? So this tangent line, this line that's just going to touch the function at 1 point, touches the function at exactly 2, 3. If you look at the point slope form, so when you look at point slope form, you can see that the point of tangency is going to be 2, 3. That's what's like really good about point slope, is that it doesn't hide that fact. Slope intercept, you'll never know. Point slope, you've got this. So here is my point, and then if I go, I'm gonna go back 1 and down 4, would put me here. And then here you can see where I messed up because I went up 1, no, over 1 and up 4. It like almost looks like it's on the curve. It's definitely not. So if I went over a half, I would go up 2. So I like really messed this up, but here's my like really careful line. Now a thing that's important about this is at the point of tangency, the tangent line and the function have the exact same value, right? They have the same y value. Also at the point of tangency, they have the exact same slope. So at and near the point of tangency, it's really hard to tell the difference between the tangent line and the function. In fact, let me do a better job by using some sort of technology to do this. What are we thinking? I think calculator, maybe. I'm a little better at zooming on the calculator than I am on GeoGebra. So I'm going to insert a new problem. I'm going to go to the graph and graph x squared minus 1. Okay, And then I'm going to graph, what are we dealing with here? 3 plus 4 quantity x minus 2. That's my tangent line. Okay, so that's pretty good, I guess. Let me put the point. So if I trace to 2, and then if you press enter, it like staples that point down and it'll stay there. Okay, so you can see they're like really close. But let's zoom box. So that's menu, whoa, God, I don't know what I did there. Menu 4 and option 2. So I'm going to zoom box around this because I'm trying to prove a point. Look at that. When you are really close to the point of tangency, the function and the tangent line are almost entirely indistinguishable. And that's one of the uses of tangent lines. We're going to use tangent lines to approximate values of functions for the simple reason that it's just easier to plug into a line. Like, why would you want to plug into a gross function when instead you could plug into a nice linear equation? So that's what we're going to deal with. That's part of what we deal with. We do so many things with this. It's very exciting. The concept of slope, the concept of tangent lines, it's a really big deal. It's like basically half of calculus. And you're starting to learn it, and I'm really excited to be there for that because this is a moment, you know. It's going to stay with you for a long time. All right, so this is just me defining a tangent line for you. I've talked about them kind of a lot at this point. So a tangent line, I feel like I'm gonna, you know, it's in a box, but this is important enough. At the point of tangency, you have the same exact value and you have the same exact slope. So the slope of the curve and the slope of the tangent line are the same. Whew, I am lagging. Okay, it's back, I think. So that's like a really important thing. I don't like the way that this color comes through on the video. It's like more green on my iPad than it is there, I think. Although that could be the tilt of my screen. Really hard to say. I don't know. Okay, use a similar process to what you've just gone through to find the slope of the curve at the point where x equals -1. Find the equation, add it to your graph. Okay, we can do that. So let's do that. So the slope, all right, so if I want the slope at x equals -1, so I know by notation that that's going to be f prime of -1. And I know because of what we did before, we're at -1, and then we have a point that's going to move closer to it. So it's like -1 plus 2, -1 plus 1, -1 plus 1/2, -1 plus 1/4, -1 plus, we call it h, but it's really delta x. So I want the limit as h approaches 0 of f of -1 plus h, which is that like outside point that's going to move, minus f of -1 over -1 plus h minus -1 is just h. And it's always just going to be h in the denominator. All right, so I got to write limit again. And let's see. So I'm gonna square it and then subtract 1. So it's the quantity, should I do it with, all right, let's do it. -1 plus h squared minus 1 minus f of -1 was, I'm pretty sure, 0 over h. So still writing limits, a lot of limits here. Limit as h approaches 0. So square, I get 1 minus 2h plus h squared minus 1. At this step, if everything that doesn't have an h doesn't cancel out, so 1 and -1, if those don't cancel out, you've done something wrong, which is part of the magic. Like, you can count on that being the case when you go through this process. And how amazing is that that will always work out? Like, it's insane, in my opinion, that always works out. If we simplify this, we just get -2 plus h, right? 1 and -1 gone. Divide out an h from everything, we get this. Now we can take the limit, we get -2. So f prime of -1 is -2. Okay, that's the slope. I also know that f of -1 is 0, so that's the point. And so our tangent line, which I'm going to write it over here, which is kind of a weird place to write it, but I have space, you know. The tangent line is going to be y minus 0. Notice I'm writing -0, even though it's 0. Ordinarily, you wouldn't do that. Point slope form, you want to make everything explicit, so you do it. It's going to be -2 quantity x minus -1, so +1. Okay, so that's my tangent line. Let's go up here. I think I did like a slightly better job. It's just like generally easier too, because like when you're closer to the vertex, it's easier to draw a quadratic. Like your brain doesn't get in the way. There's -1. The slope is -2. So if I go back 1, I'll go up 2. And if I go back 1 again, I'll go up 2 again. Get used to that. Get used to using slope in both directions. If I go forward, I go down 2. And then I'm going to try, give myself too many points. It's hard to get a line through 2 points. Never mind like a million or 4, depending on, it's all a matter of scale. But there you go. That's another tangent line. You can see when you're really close to -1. So let me highlight. When you're really close to what color should I highlight in? Any preferences? Anyone? No, I'm not hearing anything. Okay. So when you're really close to -1, the function and the line are like super close to each other. So if you had to figure out f of -0.985, right? Do you really want to square that and then subtract 1? Or do you want to plug into the tangent line, get an answer, and be like, I know that I'm wrong, but I'm not that wrong. And that's basically the idea of tangent lines. Also, we'll end up talking about, are you getting an over or an underestimate from your tangent line? Well, look at the picture. The tangent line is below the curve. That's really hard to do in this particular picture of me. It's below the curve, which means if you plug into it, you're always going to get something smaller than what the curve gives you. So you're always getting underestimates here. There's a relationship between where the tangent line falls and the shape of the curve. So in this case, we would say that this curve is concave up. So this isn't like in the notes right now, but start thinking about it. Concave up means that the tangent line is always below the curve. So if a curve is concave up, the tangent line is below, as with this. If the tangent line is above the curve, we'll say the curve is concave down. So concave up, tangent line is below, concave down, tangent line is above. I remember that confusing me when I was first learning calculus. So like it is possible that it will also confuse you a little bit for a little while, but not forever. Somehow I lost my mirroring, so I'm going to come back here. All right, so do I have any idea how long this video is so far? I do not. So instead, I'm going to do the next problem anyway. I apologize if this is running incredibly long, but I'm so excited that I didn't look at when the clock started. I don't remember when it started. All right, we did this twice. We did it once for x equals 2. We did it once for x equals -1. It wasn't terrible, but it's annoying. And what if you had to do it for like 10 different points? That would be horrifying. So instead of plugging in a specific value, what if we just had a point at x and a point at x plus something? And then we let that something get smaller. So like x plus 5 is here, x plus 3 is here, x plus 1 is here, x plus 0.1 is here. And you just keep getting closer and closer. We could do this in general. And that's actually what we're going to do. Instead of picking a specific x, let's find not f prime of 2, not f prime of -1. Let's find f prime of x. And that's going to be the limit as h approaches 0. So memorize this. This is one you memorize. Limit as h approaches 0, f of x plus h minus f of x over h. We've already done this twice. And we've done it more than twice. If you go back to the limit notes, you'll find out we did this several times. We just been picking particular values, but we don't need to do that. We can do it in general. So this will be the limit as h approaches. So keep in mind, h is the variable when you're taking the limit as h approaches 0. It's a little weird. It's really not that bad. You don't have to think about it that much, but it's good to consider. So this will be x plus h squared minus 1. That's f of x plus h. Minus, I think you should always put the function in parentheses so that you remember to distribute the negative through. That's like a big problem that I see. X squared minus 1 over h. Okay. Algebra. Basically, all limits are, well, not all. A lot of limits are basically algebra. And then once you've done the algebra, it's like you take a limit, but the limit doesn't jump in until the very last second. Then it steals all the glory away from all the algebra. But what are you going to do? All right, so we get x squared plus 2xh plus h squared minus 1, which is just hanging around. That's the thing you're going to forget, is that minus 1. Guaranteed. Minus x squared plus 1. Okay. At this step, if everything that doesn't have an h doesn't cancel out. So if there's no h involved and it doesn't cancel out, you messed up. Go back and find where you messed up. So here, I think I did not mess up. I think I got the limit as h approaches 0 of x squared minus x. Let's do a little of the old highlighter stuff. So we got x squared and minus x squared. Those are going to be gone. This is a huge highlighter. Minus 1 plus 1, gone. All right, so all that I'm left with is 2xh plus h squared divided by h. This is the reason why if everything without an h didn't go away, you'd be in trouble, because like say that 1 doesn't go away, then now you have 1 divided by h, but h is approaching 0, it's going to blow up, right? You can't divide by 0. So you need it to cancel, and you can count on that happening, and that's really reassuring. So here I'm getting 2x. So I just found that f prime of x is 2x. So let's say if f of x is x squared minus 1, then f prime of x is just 2x. Have we found that to be true? Sure we have. F prime of 2 would therefore just be 2 times 2, or 4. F prime of negative 1 would therefore be 2 times negative 1, negative 2. These are the values that we found. So this works. This is amazing. Like if I told you x is 10, you could tell me the slope is definitely 20. If I tell you the x value is negative 3/5, the slope is negative 6/5. You don't have to go through the process every time. We just derived this function from the original function by using this difference quotient and limit. The limit definition of the derivative is what that's called. Why is it called a derivative? Because we derived it, derived it has to be, right? We derived it from the original function. So this is called the derivative. And I will be back in another video to tell you a lot more about derivatives and to find some. And you know, we're just going to keep going. So it's some of my favorite stuff in math. I hope you're really internalizing it, but I hope you're like thinking about it and kind of enjoying it, because it's not a bad process, and it's crazy that we as humans have managed to come up with this. It's amazing. We can find the slope of a curve at a point. Whoever thought that would be possible? But there you go. So I'll be back in the next video, and I will see you then.